There is a building in Rome that should not still exist. It was completed in 126 AD, nearly 2,000 years ago, under the reign of Emperor Hadrian. It has no modern steel skeleton, no deep reinforced frame, no hidden network of tension cables, and yet it still stands with a presence so complete, so confident, that even today engineers walk inside it and struggle to explain how it survived. This building is the Pantheon, and above its massive circular walls rises the largest unreinforced concrete dome ever built in human history. Think about what that means. The modern world, with all its software, machines, chemical additives, steel reinforcement systems, and industrial supply chains, still has not comfortably surpassed something built by hand in the 2nd century. Modern concrete is everywhere around us. Our bridges, highways, towers, tunnels, dams, ports, parking decks, and apartment blocks all depend on it. It is the physical foundation of modern civilization. And yet, most modern concrete structures are not designed to last forever. In many cases, they are designed for a service life of 50 to 100 years. After that, cracking spreads. Steel reinforcement corrodes, water enters, repairs multiply, entire structures become more expensive to maintain than to rebuild. So here's the paradox. Why is it that a modern parking garage can begin to fail within a few decades, while Roman concrete monuments have endured for over 2 millennia? Why do modern bridges require constant inspection, endless repair budgets, and eventual replacement, while Roman harbors, aqueducts, tombs, walls, and domes still survive after earthquakes, invasions, fires, storms, and centuries of neglect? And perhaps the most uncomfortable question of all, how did the ancient world create a material so durable that the modern industrial age still seems unable or unwilling to reproduce it at scale? Because the Pantheon is not just an old building, it is evidence. It is evidence that ancient builders possessed a level of material knowledge that the modern world either lost, ignored, or buried. Every crackless curve of that dome challenges one of the central assumptions of industrial progress, that newer always means better. The Pantheon suggests the opposite. It suggests that somewhere between the Roman Empire and the modern cement industry, something extraordinary disappeared. And it was not just the Pantheon. Across the former Roman world, structures made with Roman concrete still exist in forms that modern engineers would envy. Seawalls still resist waves. Harbor piers still hold together despite direct exposure to salt water. Vaulted ceilings remain intact. Foundations remain solid. Massive walls still carry loads after centuries of stress. Some Roman marine structures have actually grown stronger with age due to the way their materials interacted with water over time. Compare that with the concrete of the modern age, which often begins its slow death the moment moisture reaches the steel inside it. This is where the illusion of modern superiority begins to crack. Modern concrete is often portrayed as the ultimate achievement of engineering convenience. It is fast, scalable, cheap to pour, and easy to standardize. But speed is not the same as longevity. Efficiency is not the same as wisdom. Our entire construction culture is optimized around short timelines, predictable costs, and industrial throughput, not around the idea that a structure should still be standing in the year 4026. The Romans appear to have built with a completely different philosophy. They were not designing for quarterly profits, short-term contracts, or replacement cycles. They were building for permanence. Their architecture assumed time. Their structures were meant to resist nature, not merely delay it. And nowhere is that more visible than in the Pantheon. Its dome, impossibly wide and eerily stable, was created without the steel reinforcement that modern engineers treat as essential. It has faced seismic activity. It has survived political collapse. It has lived through the fall of empires, religious transformation, pollution, war, looting, and the simple violence of time itself. Still, it stands. That should trouble us, because if modern engineering is truly superior in every way, then monuments like the Pantheon should be primitive relics, interesting, admirable, but ultimately surpassed. Instead, they remain embarrassing comparisons. They expose a gap between what modern industry promises and what it actually delivers. We are told that our materials are more advanced, more scientific, more optimized. But the ruins of Rome whisper a very different story. They suggest that the modern world may have traded durability for speed, resilience for convenience, and permanence for profit. And that raises a dangerous possibility. What if Roman concrete was not just different? What if it was better? Not better in every category, not better for every application, but better in the categories that matter most over centuries: durability, resilience, sustainability, and life cycle cost. Better because it did not rely on steel that rusts from within. Better because it interacted with the environment in ways modern cement often cannot. Better because its ingredients were cheaper, more abundant, and in some cases less destructive to produce. Better because it was designed to endure, not expire. If that is true, then the disappearance of this material is not a minor historical curiosity. It is a civilizational question. How does a society lose a building technology that can outlive empires? How does the recipe for a material capable of surviving 2,000 years get replaced by one that can begin failing in a single human lifetime? Was it simply forgotten during the collapse of Rome? Was it too difficult to scale? Too dependent on local volcanic materials? Or did something more deliberate happen over the centuries, as industrial systems standardized around faster, more profitable alternatives? This is where the mystery deepens. Because the story of Roman concrete is not merely a story about ancient genius, it is also a story about modern incentives. Entire industries now depend on the continuous production, repair, demolition, and replacement of concrete infrastructure. Planned service life is built into budgets, regulations, financing, insurance, labor cycles, and material supply chains. A world built around replacement does not naturally reward permanence. A material that lasts for centuries may be good for civilization, but not always ideal for industries built on recurring demand. And that is the heart of the investigation. Somewhere in the long transition from Roman builders to modern cement manufacturers, a material of astonishing endurance vanished from common use. The official explanation is usually simple. History moved on, techniques were lost, materials changed, and the modern world developed its own solutions. But that answer feels incomplete. Because when researchers began seriously re-examining Roman concrete, what they found was not a crude, primitive mixture. They found sophistication, precision, chemical intelligence. They found a material system that was not inferior at all, but in certain conditions, radically superior. So the question is no longer whether Roman concrete was remarkable. The question is why a civilization obsessed with innovation allowed a potentially cheaper, stronger, and more sustainable building logic to remain buried for so long. The Pantheon is not just an ancient monument. It is a challenge, a warning, a surviving witness from a world that may have understood durability better than we do. Its dome hangs over history like an accusation, asking why our so-called advanced age cannot reliably build what the ancient world once made look eternal. And if the answer to that question leads not to ignorance, but to industrial convenience, if this knowledge was not merely lost, but quietly buried beneath the priorities of modern construction, then what disappeared was never just a recipe. It was an alternative future. If the Pantheon is the evidence, then the real question becomes unavoidable. What exactly did the Romans know about concrete that we don't? Because this was not accidental craftsmanship. It was not trial and error stacked into monuments. It was a system, a formula, a deliberate material strategy, documented, refined, and repeated across an empire. And the first clue was never hidden. It was written down nearly 2,000 years ago by a Roman architect and engineer named Marcus Vitruvius Pollio. In his architectural manual, De Architectura, Vitruvius described something that, at the time, must have seemed almost magical. A powder, a gray volcanic ash found near the Bay of Naples, a material the Romans called pozzolana. According to Vitruvius, when this ash was mixed with lime and water, it didn't just harden like ordinary mortar, it underwent a transformation. It became stronger over time, and most astonishing of all, it could set underwater. Pause on that for a moment. A construction material that not only survives water, but thrives in it. For centuries, this detail was treated as a historical curiosity, interesting but not revolutionary. After all, modern chemistry had moved far beyond ancient recipes, or so it seemed. But then came a breakthrough that forced scientists to reconsider everything. In 2017, researchers from the University of Utah and University of California, Berkeley took a closer look at Roman concrete than anyone ever had before. They didn't just analyze surface samples, they extracted 2,000-year-old core samples from Roman marine structures, harbors, breakwaters, and seawalls that had been exposed to saltwater continuously since the height of the Roman Empire. Then they placed those samples under powerful electron microscopes. What they found changed the narrative completely. Inside the concrete, hidden within its microscopic structure, they discovered crystals, not ordinary ones, not impurities or random mineral deposits. These were rare, highly ordered formations of a mineral called aluminous tobermorite. And here is where the story shifts from engineering into something that feels almost like alchemy, because these crystals were not simply present. They were growing. Over centuries, as seawater penetrated the concrete, it triggered chemical reactions between the volcanic ash and lime. Instead of degrading the material, as happens in modern concrete, this interaction activated it. It caused new crystalline structures to form inside microscopic cracks and pores, effectively reinforcing the concrete from within. In other words, Roman concrete was not a static material. It was alive, at least in a chemical sense. It adapted. It reacted. It evolved with its environment. Every wave that struck a Roman harbor did not just erode its surface. It fed a slow, ongoing process of internal strengthening. The very force that destroys modern structures was quietly making Roman ones stronger. This is the concept modern engineers struggle to replicate. a self-healing material. In today's construction world, cracks are the beginning of failure. Water enters, steel corrodes, expansion occurs, structural integrity declines, maintenance becomes constant, decay is inevitable, but Roman concrete appears to follow the opposite trajectory. Cracks were not the end of its life cycle, they were part of it. They allowed water to enter, yes, but instead of triggering corrosion, they activated mineral growth. The formation of aluminous tobermorite and other calcium aluminum silicate hydrates essentially stitched the material back together over time. Not instantly, not perfectly, but enough to maintain, and in some cases improve, its structural integrity across centuries. Now compare that to the dominant material of the modern world, Portland cement. Portland cement is engineered for speed. It cures quickly, it achieves high early strength. It fits perfectly into an industrial system that values rapid construction and predictable timelines. But it has a weakness that becomes critical over time, especially in marine environments. Salt water is its enemy. Chloride ions penetrate the concrete. They reach the steel reinforcement embedded inside. Corrosion begins. The steel expands as it rusts, creating internal pressure. Cracks widen. Pieces break off. The structure slowly begins to fail from the inside out. And unlike Roman concrete, there is no internal mechanism to reverse this process. No self-healing crystals. No long-term strengthening reaction. Only decay. This is why modern coastal infrastructure, bridges, piers, seawalls, requires constant monitoring and repair. It is not designed to cooperate with the ocean. It is designed to resist it for as long as possible before intervention becomes necessary. But Roman engineers seem to have taken a completely different approach. They didn't fight the environment, they partnered with it. Their choice of volcanic ash, rich in reactive minerals, allowed seawater to become part of the material's life cycle. Instead of a destructive force, it became a catalyst. Over time, the interaction between water, ash, and lime created a dense, interlocking microstructure that resisted cracking and chemical breakdown. This is why Roman harbors, structures that should have been among the first to fail, are often among the most durable. Wave after wave, century after century. Instead of dissolving, they endure. Instead of weakening, they adapt. Instead of dying, they evolve. So now the mystery deepens even further. Because we are no longer talking about a simple difference in materials. We are talking about a fundamentally different philosophy of construction. One that prioritizes long-term interaction with natural forces rather than short-term resistance against them. And here's the uncomfortable part. The ingredients of Roman concrete are not rare. Volcanic ash exists in many parts of the world. Lime is one of the oldest and most accessible building materials known to humanity. The process, while complex, is not beyond modern capability. In fact, researchers today are actively trying to recreate and adapt these ancient formulas for sustainable construction. So if the knowledge is recoverable, if the science is now understood, if the benefits are undeniable in certain environments, then why is this not the global standard? Why does the modern world continue to rely almost entirely on a material system that is inherently vulnerable to time and water? Why are we still building structures that we already know will require replacement within decades, when a 2,000-year benchmark already exists? Because at this point, the story is no longer just about chemistry, it is about choice. Roman concrete reveals something that challenges the entire foundation of modern construction logic, that durability on a civilizational timescale is possible. Not theoretical, not futuristic, proven. If Roman concrete was so effective, so durable, so advanced in the ways that matter most over time, then its disappearance should not make sense. Unless something changed, not in chemistry, but in incentives. Because the collapse of Roman knowledge alone does not fully explain what came next. Techniques can be lost, yes. Empires can fall. But when knowledge is rediscovered, as it often is, the best solutions tend to rise again. And yet, when the modern construction era began to take shape in the 18th and 19th centuries, the world did not return to Roman methods. It moved in a completely different direction. In 1824, a bricklayer from Leeds, England named Joseph Aspdin filed a patent for a new material he called Portland cement. The name was inspired by the appearance of high-quality building stone from the Isle of Portland. But this was not simply a rebranding of ancient techniques, it was a transformation. Aspdin's process involved heating limestone and clay at high temperatures in a kiln, then grinding the resulting clinker into a fine powder. When mixed with water, it produced a material that hardened quickly, far more quickly than traditional lime-based mixtures. And that speed changed everything. Because for the first time, concrete was not just a building material, it was an industrial product. Standardized, scalable, repeatable, and most importantly, patentable. This is where the story takes a decisive turn. Roman concrete could not be owned. Its key ingredients, volcanic ash, lime, water, were natural, widely available, and difficult to monopolize. Its strength came from environmental interaction, not proprietary formulas. You could not lock it behind legal rights. You could not easily control its distribution. You could not build an industry around restricting access to it. But Portland cement was different. It depended on specific chemical processes, controlled kiln temperatures, defined ratios, mechanical grinding, industrial infrastructure. These were things that could be documented, patented, and protected. They could be scaled into factories, sold across regions, standardized into codes and regulations. And once something can be patented, it can be controlled. Once it can be controlled, it can be monetized. And once it is monetized at scale, it begins to shape the entire system around it. This is the intellectual pivot point, the moment where construction shifts from a tradition of public, shared knowledge into a system increasingly driven by private industrial frameworks. Now consider the timing. The 19th century was not just an age of invention, it was the age of industrial expansion. Cities were growing rapidly, railways were spreading, bridges, factories, ports, and housing were needed at unprecedented speed. The world was not asking for materials that would last 2,000 years. It was asking for materials that could be deployed immediately. Roman concrete, for all its long-term advantages, did not fit this demand perfectly. Its strength developed over time. Its reactions were slower. Its performance often depended on environmental conditions. It was a material optimized for permanence, not for speed. Portland cement solved a different problem. It cured in days. It allowed builders to pour, set, and move on quickly. It fit into schedules. It aligned with labor cycles. It supported the rapid expansion of cities and infrastructure. It was predictable, controllable, and compatible with the emerging systems of engineering standardization. In other words, it was exactly what the industrial world needed, but every solution creates a trade-off, and in this case, the trade-off was longevity. Speed replaced patience, uniformity replaced adaptability, short-term strength replaced long-term resilience. And over time, this new material did not just become popular, it became dominant. Engineering education began to revolve around it. Building codes standardized it, supply chains optimized around it, entire industries, from quarrying to kiln manufacturing to construction contracting, align themselves with this single material system. This is how a material becomes more than a product. It becomes an ecosystem. And once an ecosystem reaches global scale, it becomes extremely difficult to replace, not necessarily because it is the best possible solution, but because everything depends on it. This is what could be called the patent trap. Not a conspiracy in the simplistic sense, not a single decision made behind closed doors, but a gradual alignment of incentives where one type of material, fast, patentable, industrial, outcompetes another type, durable, natural, and difficult to monopolize. Over time, the older knowledge doesn't just fade, it becomes irrelevant to the system that replaces it. Ask a modern engineer how to design with Portland cement, and they can give you precise formulas, standards, and safety factors. Ask them how to build a Roman-style marine structure that strengthens over centuries, and the answer becomes far less certain. Not because the knowledge is impossible, but because it was never integrated into the modern industrial framework. And this is where the deeper question emerges. Did the world abandon Roman concrete because it was inferior, or because it did not fit the economic model that was taking shape? Because when you look at it through the lens of incentives, the pattern becomes clearer. A material that lasts for centuries reduces the need for replacement. A material that heals itself reduces maintenance demand. A material built from widely available natural components limits opportunities for control and exclusivity. From a purely civilizational perspective, these are advantages. From an industrial growth perspective, they are complications. So the rise of Portland cement was not just a technological shift, it was an economic alignment. A material that could be patented, standardized, mass-produced, and integrated into a rapidly expanding industrial world became the default, not necessarily because it was the most durable, but because it was the most compatible with the systems being built around it. And once that system reached global scale, the path dependency became almost impossible to reverse. Today, billions of tons of Portland cement are produced every year. It is one of the most widely used materials on Earth. Entire economies depend on it. Regulations are built around it. Careers are trained in it. Infrastructure is designed with its limitations already assumed. The world did not just choose a material, it built itself around that choice. Which brings us back to the central mystery. If a slower, more durable, potentially more sustainable alternative once existed, and if modern science is now rediscovering its advantages, then the question is no longer about whether we can build differently. The question is whether the system we've created will allow it, because escaping a technological limitation is often easier than escaping an economic one. And if the dominance of modern concrete is not just a matter of engineering, but of industry, regulation, and global supply chains, then the real barrier to rediscovering living stone may not be scientific at all. It may be structural. By now, the pattern is difficult to ignore. A material from the ancient world demonstrates extreme longevity, environmental resilience, and even self-healing behavior. And yet, the modern world builds almost exclusively with something far less durable in the long run. At first glance, that looks like a technological gap. But when you follow the money, it starts to look like something else. Because modern cement is not just a material. It is one of the largest industrial systems on Earth. The global cement industry is valued in the hundreds of billions of dollars annually. It feeds into construction, infrastructure, real estate, transportation, and national development strategies. It supports millions of jobs, from raw material extraction to manufacturing, logistics, engineering, and contracting. A handful of massive multinational companies dominate large portions of this market, operating vast networks of quarries, kilns, and distribution systems across continents. This is not a small ecosystem you can casually disrupt. It is deeply embedded into the global economy. Now, consider the nature of the product itself. Modern concrete is not designed to fail quickly, but it is also not designed to last forever. It operates within a predictable life cycle. Over decades, exposure to moisture, temperature changes, and chemical reactions gradually degrade its structure. Maintenance becomes necessary, repairs follow, eventually replacement becomes more economical than preservation. This life cycle is not hidden. It is built into infrastructure planning. Bridges are inspected regularly, highways are resurfaced, buildings undergo structural rehabilitation. Governments allocate billions every year for maintenance and reconstruction. Entire sectors exist solely to manage the aging of concrete structures. From an engineering perspective, this is practical. From an economic perspective, it creates continuity. A system where infrastructure requires ongoing repair and eventual replacement ensures a steady flow of demand. Materials must be produced again, labor must be hired again, contracts must be issued again. The cycle sustains itself. Now compare that with a hypothetical alternative, a material that significantly extends structural lifespan, perhaps doubling or tripling it in certain environments, a material that reduces maintenance frequency, a material that performs better in harsh conditions like seawater exposure. From a civilizational standpoint, that sounds like progress. From an economic standpoint, it introduces friction, because if structures last much longer, replacement cycles slow down. Demand becomes less predictable. Entire segments of the industry, maintenance, repair, reconstruction, would begin to shrink or transform. This does not mean there is a coordinated conspiracy, but it does highlight a tension. The incentives of long-term durability do not always align perfectly with the incentives of large-scale industrial systems. And this tension shows up in more subtle ways. Take education. Modern engineering programs are built around standardized materials and methods. Students learn formulas, safety factors, and design codes that are based on Portland cement systems. These standards are reliable, measurable, and well documented. They allow for consistency across projects and regions, but they also create a kind of intellectual inertia. Roman concrete is often treated as a historical curiosity, interesting, but not central to modern practice. Its variability, dependence on specific materials like volcanic ash, and long-term reaction processes make it harder to standardize within modern engineering frameworks. As a result, it rarely becomes part of mainstream training, not because it has no value, but because it does not fit easily into the system that exists. Now consider regulation. Modern construction depends heavily on certification standards. Materials must meet strict criteria for strength, durability, safety, and predictability. Organizations like ASTM International and similar bodies worldwide define these benchmarks. Without certification, materials cannot be widely adopted in critical infrastructure. And here's the challenge. Ancient recipes, like Roman concrete, do not come in standardized one-size-fits-all formulations. Their performance depends on local materials, environmental conditions, and specific mixing techniques. That makes them difficult to fit into modern certification frameworks, which rely on repeatability and uniformity. So even if a material shows extraordinary long-term performance, it faces a barrier, not necessarily because it fails, but because it does not conform. This creates what could be called a regulatory wall, a system where only materials that meet predefined industrial standards can be used at scale, standards that were built around existing materials in the first place. Breaking into that system is not impossible, but it is slow, expensive, and uncertain. And when an industry is already functioning, already profitable, already optimized, there's little immediate pressure to take that risk. So the result is not an obvious suppression, it is something quieter, a combination of economic inertia, educational focus, regulatory structure, and industrial investment that keeps the current system in place. Roman concrete is not banned. It is simply sidelined, studied in research papers, recreated in laboratories, occasionally tested in niche applications, but rarely adopted at the scale of highways, skyscrapers, and global infrastructure networks. And that brings us to the real question. If a material exists, or can be recreated, that offers greater longevity, better environmental interaction, and potentially lower life cycle costs, what would it take to actually replace the current system? Because changing a material is not just about chemistry. It is about retraining engineers, rewriting building codes, reconfiguring supply chains, reinvesting billions in new processes, and most importantly, accepting a shift from short-term efficiency to long-term thinking. That is not just a technical challenge, it is a structural one. So when people ask why we don't already use something like Roman concrete everywhere, the answer is not as simple as it was lost or it doesn't work. The more honest answer is this: the world built a system around a different set of priorities, and systems, once established, do not change easily, no matter how compelling the alternative may be. Which leaves us with a final, uncomfortable realization. The greatest barrier to building structures that last for centuries may not be a lack of knowledge, but a lack of alignment between what is possible and what the system is designed to support. After everything we've uncovered, the Pantheon's impossible endurance, the chemistry of living stone, the industrial shift towards speed, and the economic gravity of modern cement, one final question remains. What would it actually take to build like the Romans again? Because this is no longer just history, it's a choice. At its core, the Roman formula is not mysterious anymore. The ingredients are surprisingly simple, almost uncomfortable in their simplicity. A mixture of volcanic ash, hydrated lime, rock aggregates, and in marine environments, seawater. That's it. No steel reinforcement, no ultra-complex chemical additives, no high-energy industrial processes in the modern sense. But the real intelligence was never just in the ingredients. It was in how they were combined. The Romans understood that volcanic ash, rich in reactive silica and alumina, could chemically interact with lime to create long-lasting mineral bonds. They selected aggregates not just for strength, but for how they would react over time. In coastal structures, they allowed seawater to penetrate the material, triggering slow crystallization processes that reinforced the structure from within. They were not building something static. They were building something that would continue forming itself after construction. Today, we don't always have access to the exact same volcanic materials found near ancient Roman sites, but modern science has already identified viable substitutes. Materials like metakaolin, calcined clay, and even certain types of coal fly ash can replicate many of the same chemical behaviors. These are not theoretical ideas. They are actively studied and, in some cases, already used in specialized construction projects. In other words, the barrier is no longer knowledge. We know how this works. We know what materials can achieve similar effects. We know the long-term advantages in specific environments, especially in marine and high moisture conditions. So the question shifts again from can we do it to why aren't we doing it at scale? And this is where the economic argument becomes impossible to ignore. Because when you strip away branding, industrial layers, and global logistics, Roman-style concrete is not inherently expensive. In fact, in certain contexts, it can be significantly cheaper in raw material terms. Lime production can be less energy intensive than modern clinker production. Supplementary materials like calcined clays or industrial byproducts are often abundant. The absence, or reduction, of steel reinforcement further lowers cost in some designs, but raw cost is only part of the equation. Modern cement carries hidden expenses: maintenance, repair, corrosion management, and eventual replacement. These costs are spread over decades, often absorbed by governments, taxpayers, and future generations. When you calculate life cycle cost, the picture changes dramatically. A structure that lasts 80 years and then requires replacement is not cheaper than one that lasts 300, even if its initial cost was lower. This is the difference between building cheaply and building wisely. And quietly, in parts of the world, this realization is starting to take hold. Across Europe and other regions, a small but growing number of architects, researchers, and independent builders are experimenting with alternative concrete systems. Not always pure Roman replicas, but inspired by the same principles. They are reducing cement content, reintroducing lime-based mixtures, exploring pozzolanic materials, designing for longevity rather than minimum compliance. It's not a revolution, it's a quiet rebellion, small scale, often overlooked, sometimes dismissed as experimental, but driven by a different philosophy, the idea that buildings should not be disposable objects, but long-term assets, that infrastructure should not be designed with an expiration date, that sustainability is not just about reducing emissions today, but about avoiding reconstruction tomorrow. And this is where the story comes full circle. Because the rediscovery of Roman concrete is not just about reviving an ancient recipe, it is about confronting a modern mindset. For over a century, construction has been optimized around speed, cost efficiency, and scalability. These priorities built the modern world, but they also created a system where durability is often secondary, where replacing a structure is expected, where good enough for now becomes the standard. Roman builders operated differently. They built with the assumption that their work would outlive them, that it would serve generations they would never meet. That time itself was not an enemy to resist, but a factor to design for. So the real question is not whether we can recreate their materials. We can. The real question is whether we are willing to adopt their philosophy, because choosing a more durable path may mean slower construction. It may require new standards, new training, and new supply chains. It may challenge industries built around constant renewal. It may force us to think in terms of centuries instead of decades. And that is not just a technical shift. It is an ethical one. Every bridge we build, every building we pour, every coastal barrier we construct, these are not just engineering decisions. They are commitments to the future. They determine how much future generations will need to repair, replace, or rebuild.